Problem number 7. Let R be the unit square in the plane with vertices 0, 0, 4, 0, 0, 4, and 4, 4. We're given a table of values here. I'm not going to write down. We are going to be estimating f of xy, the double integral of f of xy, over this region right here. So 0, 4, 0, 4 here. So how do we go about estimating our the double integral here? What we're going to do is that we're going to do a kind of two-dimensional Riemann sum estimate. I went ahead and broke up the big square into 4 smaller squares. Note that each of these squares has area 4. And we're going to estimate the function on each one of these smaller subsquares by a value of our f of xy at one point in the square. There's different possibilities that we could try here. As one possibility, let's ask ourselves, what estimate do we get if we always estimate the value of the function on each smaller square by the upper right point here, the upper right corner? So reading off of our chart, let's see here. This would be f of 2, 2. Off of our chart is 3. F of 2, x is 2, y is 4. This would be 2. F of 4, comma 2 would be 2. F of 4, comma 4 would be 1. So our estimates here, what estimate is this going to give us on the, we have to do the multiplication of the area of the box by the function value estimate on that box here. So area is 4 times 2. This one would be 4 times 1. This one would be 4 times 3. And this one would be 4 times 2. And if we add all of these up, 8, 12, 24, and 8 more is 32. And that is one of our choices here. 32 is one of our choices, and so we'll go for that one. Now, you might wonder, well, there is nothing, why did we choose to go with the top right? We could have made a different choice here. Let's just make a different choice. Let's go with the top left instead. So if we estimate this box with this point, the function on this box with this point, and so on. So this function value here, that would be f of 0, comma 4 is 1. We already know that f of 2, comma 4 is 2. This one right here, f of 0, comma 2 is 2. And f of 2, comma 2 is 3. And so 4 times 1 plus 4 times 2 plus 4 times 2 plus 4 times 3 again gives us 32. And I think that no matter which estimate you use, the top left, the top right, the bottom left, or the bottom right, you end up with 32. So we should be feeling pretty good about a 32 estimate, especially because the next closest answers that we are allowed to choose here are off by a factor of 2 here. Okay, let's take a look now at this problem. Integrate f of xy as x squared plus y squared to the negative 3 halves power over the region that is defined by these bounds here. We're supposed to do this using polar coordinates. Okay, so let's go ahead and draw the picture. This will be very difficult if we aren't drawing the picture here. X squared plus y squared is less than or equal to 1. That is, we are inside a circle of radius 1. X plus y is greater than or equal to 1. The line x plus y is equal to 1 is the line that goes through the points 0, 1, and 1, 0. And so we are inside this circle, but above and to the right of this line here, this is the region that we're integrating over. Okay, how do we go about doing this? We need bounds on r and theta here. So for theta bounds, we can see that theta can take on any value from 0 to pi over 2. That's pretty straightforward. For r bounds, the biggest r can be here. The biggest r can be is 1. The smallest r can be is when we hit the line x plus y is equal to 1. And so that's going to be a different value for different values of theta. So, if theta is 0, the smallest r can be is 1. If theta is pi over 2, the smallest r can be is 1. But if theta is between 0 and pi over 2, the smallest r can be is some number that is less than 1. So what we're going to do, we're going to take this bound, x plus y, we're going to take the line x plus y is equal to 1, we're going to convert this into polar coordinates. So this becomes r cosine theta plus r sine theta is equal to 1. We want to solve for this r in terms of theta. R times cosine theta plus sine theta is equal to 1. So r is equal to 1 over cosine theta plus sine theta. Okay, so this is our lower bound on r. And so at this point then, we are able to set up our double integral. Theta runs from 0 to pi over 2. R runs from 1 over cosine theta plus sine theta to 1. Now, we have to convert our integrand here. X squared plus y squared is r squared. So this is r squared to the negative 3/2 power. And that is r to the negative 3rd power. And then we throw in the r dr d theta. So don't forget to throw in that factor r here that's coming from the Jacobian when we do the polar coordinates transformation. R to the minus 3 times r is equal to r to the minus 2nd power. So let's go ahead and evaluate this double integral here. Antiderivative r to the negative 2nd power is minus r to the minus 1st power. We are plugging in. R runs from 1 over cosine theta plus sine theta to 1 d theta. And so what do we have here? When we plug in, r is 1. We have minus 1. Then there will be a plus sign here. Minus times minus is plus. 1 over cosine theta plus sine theta to the negative 1st power will just be cosine theta plus sine theta. And so this is the integral we need to evaluate here. This should be a straightforward process. So let's see. We'll have negative theta plus sine theta minus cosine theta is our antiderivative. Plug in theta running from 0 to pi over 2. And so this will give us negative pi over 2 plus 1 minus 0 minus 0 plus 0 minus 1, or 2 minus pi over 2. And so this is our final answer to this problem.